In this video we're looking at superposition, and specifically we're talking about constructive and destructive interference. So we're talking about different waves when they interact. I shouldn't say the term they collide because they're not physical objects necessarily that are smashing into each other, but we can think of it in that sense. When two waves run into each other, what happens? And this is the concept of superposition. So superposition of waves means that they interact or they react with each other. There are three main options when waves interfere. They can either amplify each other, and we call this constructive interference. They can cancel each other out, and we call this destructive interference. Or they can do some sort of combination of both, and we'll talk about some aspects of that towards the end of this video. If we have a crest and a crest, so firstly, the crest part of the wave is the peak point. So we talk about the crest, and the trough is the bottom point, which is not shown on these diagrams. So when we go up, we have a crest. When we go down, we have a trough. You can think of it as a trough goes down, like a water trough. It's a bowl-shaped object, so that'll help you remember. If we have two crests that have the same amplitudes and they interact with one another, so just like this, we've got the two crests, they run into each other. In this case, we can see that the amplitude is just the sum of the individual amplitudes. So when they pass through each other, they amplify, and suddenly you get, in this case, you get an A plus B amplitude, so it is increased. And what we would observe in the real world, a physical observation, would be an increase in volume. So if we played this frequency or this note, and when the two waves collide, there would be a point at which the sound gets louder. And then they would pass on and keep doing their thing without any effect after the interaction. So the waves aren't consumed or anything like that. They just pass through, amplify, and then carry on again. So for constructive interference, the waves are on the same positive or negative displacement point when interacting. So they both have to be at a crest or a trough when they pass through. The amplitudes are added together, so it's just the amplitude of A plus the amplitude of B, and then the waves continue on after the interaction unaltered. That's an important aspect. If we then take a slightly different case and we have a crest and a trough, when a crest and the trough of the same size interact with each other, we get this destructive interference, and this is basically a cancelling out. The crest part tries to displace the spring upwards. If this is what we're talking about, we've got a spring that we've sort of flicked up and down. This part is trying to push the spring upwards, and this part is trying to pull the spring down. So just like when we add forces, you've got like a positive force and a negative force, and the quantity is exactly the same, so they cancel them out. So at the point where they interact, the A plus B is actually A minus B because of its direction, and you get zero. So we would observe this as a dead spot. So if you were to stand right at this point where the two waves ran into each other, you would hear nothing. And then a fraction later, if you shifted, the waves continue on again unaltered, and you have sound again. So the waves collide when they're opposite. You've got a trough and a crest. They cancel out, so you get zero displacement. You get this zero amplitude, zero sound. The principle of superposition is all about this constructive, destructive interference. It's all these combinations of waves. It allows us to determine the resultant shape of a wave when we have two or more waves that are running into each other. We can predict, without actually measuring using some sort of an apparatus, what that wave would look like. So when waves coincide, the resultant wave amplitude is the sum of the amplitude of each incident wave. And that's the same for destructive and constructive. You just need to remember that for destructive, one is a negative sign. An example of this that you can see, and there are some worksheets available on this, if you were to use graph paper to represent this, say we had a wave that was given like this, so its maximum amplitude is 2 centimeters, it's got a little 1 centimeter piece, a flat spot, and then a 2 centimeter down, and it runs into a wave that has a 2.5 centimeter amplitude with a 5 centimeter gap. It's a triangular wave in this case. So this is a bit of an abstract case, given that you've got different wave shapes, which you can absolutely have. You can have square waves and sawtooth waves and all kinds of things. But we can mathematically draw this using graph paper. So we draw a scale version of the original and a scale version of the original of B, and we draw them over the top of each other, A being up and B being down, and we just look at all the points, and each point is a sum of its individual points. So here we had 1, 2, 3, 4, or just shy of 4, and here we had 2 down. So the resultant would be a +2 up, and I do this for all of the significant points, and I end up with this resultant wave. So we draw the pulses coinciding over the top of each other. We figure out the sum of all the key points, so basically every sort of point on the actual wave. We record these the displacement, and then we draw the line to fill in the dots, and we've got our displacement. So this is the new superposed wave that results from these two. And you can do this for a whole range of examples. If we look at incomplete superposition, this is where we get a phenomenon known as beats. And beats is sort of a situation where the waves are not constructively or destructively interfering. They're actually creating this whole new sort of effect altogether. And this video will explain that in a little bit more detail.
Beats are changes in amplitude when you have two waves that have a frequency that's very close together. And you can actually play around with this if you're connected to the internet. And so I'll put a link to this down below. But if you go to this website right here and you launch it, what you can do is you can play a tone. And so what I'm going to do is play one that's at 440 hertz. I'm then going to launch another tab, and in that tab I'm going to briefly change what note I'm playing. So that's 440 hertz. That's also 440 hertz, but listen what happens when I change one of them. Those are beats. Now they're gone. Now as I go above it, you can hear the beats again. And as I bring them back to the same value, then it goes away. Now, when would this be useful? Well, let's say you're tuning your guitar. What you can do is tune one of the strings. So make sure you tune that to a tuner or a piano or something like that. Once you have that, then you can play another string. You have to move up on the fret, but play another string. And if it's close, you'll hear the beats. And if it's exactly the same, you can adjust the one, then the beats will go away. And then you can move on to the next string and the next string and the next string. And so waves, when they come together, will interact. And as they interact, they cause interference. Now that interference can be constructive, sometimes building up the wave or the summation of the waves, and sometimes it's destructive, it's tearing it down. But if those waves are very similar in frequency, what you get are these beats, and beats are going to be amplitude changes. In other words, the volume is going to go up and down and up and down and up and down due to this constructive and destructive interference. Now it's really easy to calculate the frequency of the beats. All you do is frequency of the beat equals the absolute value of the difference between the two frequencies. So if I know frequency 1 and 2, I simply subtract 1, and it's the value, absolute value of those. And so again, in review, if you don't know what constructive and destructive interference are, if we have two waves that are perfectly the same frequency and they're right next to each other, what we'll get is constructive interference. If they're out of phase with one another, we'll have destructive interference. But if the frequencies are slightly off, and if we look at this animation down here, these are frequencies that are close but not exactly the same. What you get is, as you have this constructive and destructive interference, you get the blue summation of those two waves, and you can see that we're seeing these changes in the amplitude. In other words, the amplitude is decreasing, then increasing, and then decreasing. Now, if I could make those frequencies exactly the same, then the beats are simply going to go away. How do you calculate it? Again, it's frequency 1 minus frequency 2, absolute value of. And let's do a sample of that. So I'm using Audacity. It's a little music software. And so what I'm going to do is I'm going to generate some tones. And so I'm going to generate a 440 hertz tone. So that'll be in one track. And then I'm going to add another track down here, and we're going to generate another tone. So we'll make this one slightly different. It's 440 hertz. Like that. Now let me mute the bottom one and play the top. And now let me mute the top and play the bottom. So they sound almost the same, but let's play them together now. So we'll unmute them. So now you can hear those beats or those changes in the amplitude. Now let's calculate what the frequency of the beat should be. So frequency of the beat is going to be F1 minus F2. And so what were the two frequencies? Well, we had 440 and 444. And so if I put those two values in, what's my frequency of the beat going to be? It's simply going to be 4 hertz. So now let's check that with this model. And so what I'm going to do is now mix these two together, and we're making a single track of the two. And now let me get rid of those first two tracks. You can already see the beats. And now let's check our numbers. So let's look at 1 second in time. It's exactly 4 beats. The frequency of the beats equals the difference between the two frequencies.
Okay, so basically when we have two waves that are coinciding with slightly different frequencies, we get this entirely new wave pattern, and this is what we call beating. So it creates that sort of pulsing, beating sort of sound that we hear. And it's not from a beating, pulsing signal, it's from that interference that's changing how it works. So it interferes one moment, it doesn't the next, interferes one moment, and it oscillates that process. And this is where we get beats. As I said in the video, we use this a lot for instruments. We use this to tune pianos, guitars, things like that. And you can do it a few different ways. You can use a tuning fork that has a known frequency. So if you have a tuning fork that is a C note, you can strike the tuning fork and then strum the C note on a guitar, for example. And if you hear that beating sort of sound, you adjust the tension in the string until that beating goes away, and then you've perfectly matched the frequency. And it's quite accurate, as you saw in that video. Just by changing by 4 hertz, you could hear the beat. So that beating effect is audible, although we may not ordinarily be able to pick by the ear what exactly a C note sounds like. We can use this beats to get a much more precise application. Another example of something where you see beats occur is with twin-engine aircraft. Because you've got both propellers or engines spinning at the same time, but one may have a very, very slightly different frequency to the other. And this creates that oscillating drone that you hear. Sometimes you might hear it in a general sort of commercial airline, but particularly with propeller style, it's a lot more common to have that beating effect because of the two propellers interfering with each other by not being the perfect frequency. In the video, Mr. Anderson mentioned something called phase. So phase is just when we have two waves that have the same displacement and direction, and they're basically aligned. So whenever one source reaches its crest, the other source does the same thing. And conversely, when it reaches the trough, the other one does as well. So here you can see this is two waves drawn over the top of each other, and this one reaches a crest when this one reaches a crest. Trough, trough, crest, crest, etc. So we would say that this is in phase. The waves are perfectly matched. So they're reaching the same point. If this is a time axis, they're reaching the same point at the same time. If we want to say it's out of phase, then we've just shifted one wave left or right so that the crest does not perfectly align with the crest. And you can see that here. This wave has been shifted by this distance. This is its original resting point, and this is its resting point. So the distance between those two adjacent points, kind of like when we talked about a wavelength, here we say just the distance between the 2 points that match on the two waves gives us the phase shift. So that's how far off of being in phase it is. And if we go completely out of phase, as you can see here, we've moved the entire thing by half a wavelength. So here when I was at the top, I'm at the bottom. So I've shifted by what we would say lambda on 2, a full wavelength divided by 2, half a wavelength. And this is exactly where I get my destructive interference. So destructive interference, and here would be constructive interference, is linked exactly to the phase. If I'm in phase, I can constructively interfere. If I'm out of phase, I can destructively interfere. And if I get somewhere in between, some version of being out of phase, this is where I can see that beats effect occurring. Coherence is another common term that we use in terms of light and waves. So if two waves are out of phase, they can still be coherent. And what that means is that there's a constant relationship. So whether they're in phase or out of phase, it doesn't matter. But as long as they maintain that phase shift the whole time, we say that they are coherent. So the offset is constant the entire time. An example is this one here. So you can see that it's at a peak when it's sort of halfway down. Next time it's at a peak, it's still halfway down, still halfway down, still halfway down. So it is wave shifted by, in this case, it's probably a little over half a wavelength, because this point here would be half a wavelength, but it's a little bit more than that. But it's maintaining that the entire time. So this would be out of phase, but it is coherent source. So in order to do that, we need the waves to have the same frequency, because if the frequencies aren't the same, they're never going to be constantly aligned with each other. One is shifting at a different rate. They need to be moving at the same speed for the same reason. Even if they're the same frequency, but one's moving faster, it's going to start to catch up or drag behind, and that shift will change. And it obviously needs the same wavelength. Just as it needs the same frequency, the distances that way have to be the the same as the shift between the phases. So same frequency, same speed, same wavelength. The amplitude is not important here though. Remember, amplitude is purely just volume. If we want to talk about sound, it's the energy. So it doesn't matter if this one is a larger amplitude, it's a louder signal. As long as the pattern, the crests and the troughs or whatever are still the same shift, they are still in phase. Some common examples are sunlight. So sunlight is neither coherent nor in phase, and it's a whole range of different colors. So we know that it makes up the whole color spectrum, the visible light, which are all different frequencies for a start, so we know that it can't be coherent. And they're not in phase because they're all in different directions and there's no sort of consistency there. LEDs, however, are, for example, a monochromatic LED. It's a single color. They're not in phase either. So they're monochromatic, which we haven't talked about yet, but it just means they're a single color. But you can see from here they're not in phase, so they're constantly sort of changing their relationship. A laser, however, is monochromatic, so it's a single color, but it is also in phase and coherent. So we have this pattern where it's in phase, so it's a peak and a peak and a peak. It's perfectly aligned, it's in phase, and it's coherent because this relationship is maintained the entire time. So there's some examples of that. A standing wave is where we basically have a wave where one end is fixed. Every time we go towards the fixed end, as we would see, the wave pulse comes up, but when it gets to the end, what it does is it reflects. So if it's coming up, it's going to then sink back down, bounce off the wall and come down on its way back. So it creates this effect that when one point is fixed and it can't move, as the wave comes back, it basically sort of cancels itself out, and you have this momentary section where the wave is flat, goes up, goes down again. And so this creates this continuous wave train moving along the spring in the opposite direction as it reflects. Given that the reflected wave has identical frequency, wavelength, and speed, this is why we get this standing wave pattern. The amplitude realistically would be slightly smaller on the reflection, as we're losing energy both on the rebound and over distance. In these representations and a lot of the simulators, you can change how much we lose, but we generally say it's fairly negligible, so that most waves have an identical amplitude. So you may notice that there are points on this wave, which are the red dots, that aren't actually moving. So even though this is a wave, we've got points that are not moving up and down, which is different to what we talked about earlier when we had traveling waves, where every point is moving up and down. Now when we've got a standing wave, which is kind of why we call it a standing wave, we have points that are not moving. They're standing still and everything else is oscillating back and forth between it. And this is because when we talked about an ordinary wave or a pulse, we didn't have that perfect reflection coming back from the fixed end. When we have that perfect reflection, it cancels consistently, and so these points don't actually need to move because they're constantly being opposed by the incoming wave. If you think about it, as this wave comes down, this one comes up, and so they're always cancelling at every point in the wave. The important terminology here is that we call the point where the wave does not move, we call that a node or a nodal point. And where we have the maximum movement, the highest point where it goes up and down, we call them the antinodes or the antinodal points. So nodes, no movement, antinodes have movement. And this pattern, this concept here is what we call the standing wave, where, as we said, different to the traveling wave, every point oscillates in a traveling wave. In a standing wave, only the antinodes move. From here, have a look at the workbook questions on superposition. If you've finished those and you've finished the previous chapter's questions, have a look in the physics workbook, and there are some more questions on superposition there that you can do to look at whether you get a constructive, a destructive, or some sort of a hybrid combination of a wave pattern as a result of that. And I'll see you next lesson.